Good morning. The title has already been presented by Professor Kuna. Thanks for the introduction. And I will focus my presentation today on new biaxial specimens. I will show some slides regarding the intentions, the ideas, and show some experimental and numerical results. First of all, I would like to stress that I will talk about ductile damage and fracture. So we have to keep that in mind. What is damage in our understanding? Damage is an ongoing process which leads to final fractures in ductile matter. So for high positive stress biaxialities, we have void growth as leading damage mechanism, and we have the appearance of micro shear cracks below a certain cutoff value. Below we have no damage occurrence, and we have this intermediate zone. So let's have a look at the phenomenological model. Which material behavior do we assume to have? We have first pure elastic material behavior till we fulfill the yield condition. Then we have elastic plastic material behavior till we fulfill a damage condition. And then we have elastic plastic damage material behavior, which finally leads to a macro crack. So just very briefly about the continuum damage model. There were a couple of papers published. I took 3 of them indicated here. So what does the continuum damage model consist of? We have the introduction of damage and fictitiously undamaged configuration. So we have the kinematic definition of damage dampers and damage strains. We have different elastic potential functions. We have a yield condition and a corresponding flow rule. And we have a damage condition and an anisotropic damage rule. So within this model, we have a whole bunch of material parameters which have to be identified. We did a series of micromechanical studies on reference volume elements. And we got an idea of the material parameters, but still the experimental validation is pending. So we now focus on experiments to validate the continuum damage model, which is a big challenge. So I would like to review, brief review on specimens. I will restrict myself here for sheet metals and in plane loading. So first we have the standard dot hole specimen where we can introduce different notches. So with increasing notch radius, we have increasing stress biaxialities in the center here. But still it's important to point out we have stress gradients here. We don't have a uniform stress state here. A similar idea is proposed by the central hole specimen. You can change the diameter or the radius of the central hole, and you have different stress states here in the center. But here you have also deformations on the border, while here you have the middle still staying straight. Different option you have is using this plane strain specimen where you can put a big notch on both sides, and you have a very pretty homogeneous stress state here, at least in the center area. Having a look at shear mechanisms, which are very interesting to study experimentally. You can see here this old proposal, very strict boundary conditions, very rigid, to force the specimen to have shear mechanisms in the central part. And that is what we found proposing these geometries. We first started out with an unnotched version, and we had very big rotations here of the central part. So we didn't have shear mechanisms, but leading rather to tension mechanisms. By introducing notches, we could concentrate that, but not completely avoid. This specimen, and there are several others in the literature, has the same idea than we have shown here. Another different idea came up here very early, also in 1984, with 2 regions of shearing. This
This is an idea which avoids big rotations in the central part due to the symmetry. An idea which has been picked up here in this geometry. Okay. Tension shear specimens. Oops, there's a picture missing here. You should see the Arcan specimen here, which is very similar to this one, where you can load in different directions and you have shear or compression shear or tension shear in the central part. Here this small notch was introduced. And a similar idea you can find in this butterfly specimen, which can be loaded also in this direction and in the same time in this direction, causing different stress states and different deformation histories here in the central part. Now, having a look on biaxial specimens, that is what I will focus on later on. And if you look in literature, you find basically these cruciform specimens where a lot of work has been done into optimizing these areas here where the leg comes into the central area, or putting here these slits in, or reducing the thickness in the central area. But the main focus of all these specimens is to validate plasticity, to validate the beginning of plasticity, the flow rule, or the initial part of flowing, of the plastic flow. All these specimens tend to localize. So you get either fracture here with a rupture of one leg, or you get concentrations here, depending on how you load it. So it's difficult because damage and afterwards a fracture is a rather tending localized process. So we came up with some ideas. Have been published also already. We came up with these, I call now Z specimen due to the form. And it's a combination here. You can see loading it in this direction. You have a rather tension dominated stress state here, and loading it in this direction. You have a rather shear dominated stress state in this here in this central area. So now you can load it first tension and compression, or in both ways, similar at the same time, and you get different stress states in the center. Unfortunately, you have a strong coupling between two legs, which is from the experimental point of view very difficult. Your machine has to be able to support, if you load tension here, you get forces in this direction, and your machine might not like that. We had that experience. So be aware of using this specimen. So we came up with other ideas. This is the XO specimen, we call it. It has a central hole, and it has 4 independent notched regions. So you can load one direction always in tension, and the other you can superimpose tension or compression, causing different stress states in the notches. Similar idea here. You have 4 notches. This is what we call the H specimen. You load this always in one direction, causing shear mechanisms here, and you can superimpose tension and compression. So it will lead to different stress states here. Well, first you think, well, 4 different notches. These are behave very similar during the experiment, and we found out that they do behave very similar during the experiment. Later on in this talk, I will focus and present experimental and numerical results of these H specimens. Okay, briefly on the aluminum. We are right now working on an aluminum series 6000. Here you can see a force displacement curve, and you can see we reach here maybe strains to around 16 to 20%. So it's not very high strains. You will find more ductile materials. And the other thing is you don't have significant hardening here, which is also difficult in the experimental behavior, during the experiment. It's it's nicer or it's easier to do the experiments if you have hardening. So, but now we are with this material and we trying to manage. The machine, how it looks like, at least how it looked like a few years ago. Here you have 4 independent cylinders, which can do 20 kilonewton compression and tension loading. If you decide to buy a machine yourself, maybe you buy one for 50 or 100 kilonewton, because this is a pretty big restriction for the design of your specimen. But well, this is the first machine Walter and I built in this way, so we are happy to have it and we can do the things we want to do. I said it's the machine as it was a couple of years ago, but I still kept this old picture because we now built a pretty big digital image correlation system around it. We have lighting systems here, so everything got very crowded on the table and even beneath the table, because we arranged to have 2 cameras from below and 4 cameras from above. So it's easier to see on this photo how that works. Okay, again, focusing on the H specimen. Here it's a photo of it. It has legs which are 240 millimeters in each direction. Here in the sketch, more in detail, you can see the central area with the measurements. And here, this way, and you can see that the notch has a radius of 2 millimeters, and the initial thickness was 4 millimeters, and we have 2 millimeters remaining. Some global results. Here we see load displacement curves of this direction. So we have here a reduction of forces with ongoing tension or even with ongoing compression. We have buckling below -1 for the specimen. That is why only these load cases are presented here. Here you can see by the diamonds, blue diamonds, the experimental points, and the black is maybe an approximation of it. Fracture surfaces. 1 minute. Fracture surfaces. You can see here a very coarse or very rough potential loading, and it becomes more, more direct or more fine by shear loading. And also the direction change. I will skip one of the movies because I have only 1 minute and try to start this movie. Yeah, it's tension, or it's loaded in this direction and compression in this direction, and you can see shear bands or deformation going on here, pretty homogeneously. And finally, fractures. Okay, brief on the stress triaxialities or the tension or load parameters. It's very homogeneously distributed in the central area, and you can get a wide range of stress triaxialities. With these uniaxial specimens, we can reach only certain points of stress triaxialities, and with these specimens, we can manage to have a big variety of stress triaxialities. Finishing, we had an overview of specimen geometries. I've shown experimental and numerical results with the H specimen, and the perspective would be specimen geometries for thin metal sheets, where we can have the notch and thickness direction, other materials, and linking back to experimental data to the continuum damage model. Thank you for your attention, and maybe in the end we are able to have questions.